Okay, good morning to all of you. I welcomes to all in our lecture series on electromagnetic theory, that is your core paper 13 6th semester BSc syllabus. In our last class we have been discussed this topic, that is your wave propagation characteristics in good dielectrics. Attenuation constant alpha, we found this much, and for ideal good dielectrics the conductivity will be 0, so alpha will be 0, and we derived phase shift constant beta, velocity propagation vp, velocity of propagation vp we found, and wave propagation characteristics in good conductors also we have been discussed. And here also we found alpha, beta, and uh, alpha and beta, and another alternative method also we found same alpha, beta, and then we have been discussed the velocity of propagation in conducting medium, that is your 2 omega mu sigma, 2 omega by mu sigma whole root over. Now today we are going to discuss depth of penetration, which is symbolically represented by delta, or it is also called as the skin depth, right? And before that, a small physical parameter that we are going to be discuss, that is your refractive index. Okay, we know that the refractive index of of any medium. See, when the wave is electromagnetic wave is penetrating any medium, then also we have to find out the refractive index that medium. Okay, so refractive index of any medium, in generalized way, it can be defined as velocity of electromagnetic wave in vacuum by velocity of electromagnetic wave in that medium. Okay, so velocity of wave in vacuum, we know that c, that is your velocity of the speed, divided by, here we consider the medium as your conducting medium. If we are going to consider the conducting medium, then the velocity of electromagnetic wave that we found 2 omega by mu sigma root over, that we have to put over there. Then we can found the refractive index of a conducting medium will be this much. Okay, that is your c into mu, that is a permeability conductivity, by 2 omega is nothing but your angular velocity with which the electromagnetic wave is propagating that in that conducting medium. So just remember this terms, that it will be help you to solve the numericals. So now we have to discuss the depth of penetration, or that is called the skin depth, represented by delta symbol. So here, this is the definition of your penetration depth of penetration or skin depth. The definition is, the depth of penetration is defined as that depth, okay, at which the wave attenuates to or reduced to, attenuation means reduction, attenuates to or reduced to 1 by eth time, or approximately 37% of its original amplitude. What is it? And it is denoted by symbol delta, and unit is meter. Here I am going to be show you what is happening. See, without attenuation, electromagnetic wave is starts to penetrate inside a medium. Suppose this is your medium, another medium, and this side is your vacuum. Okay, this side is your vacuum, and electromagnetic wave in the vacuum, it is traveling without attenuation. So when it is striked, or when it is interacted the interface, this is the interface, okay, where both the medium are connected. When it is interacted the interface, at that point the amplitude is E0. This is your maximum amplitude E0. But when it starts to penetrate, then its amplitude starts to attenuation. Attenuation means it is starts to decrease. So as it is moving inside a medium, then its amplitude gradually decreases, and at a particular length it will be reduced to 0. But according to depth of the penetration, at which distance, suppose after traveling this distance, its amplitude originally it was E0. At this distance, its amplitude reduced to 37% of E0, or you can say that E0 by E into 100 equal to 37%. See, E0 by E0 by E, what it is written, 1 by eth time of its original amplitude. Okay, 1 by, this is your original amplitude, 1 by eth, and E value is around 2.37, right? So you can found 1 by 2.37 value is approximately 0.37, okay. So 0.37, if we are going to multiply it here 100, then it will be 37% of E0. 37% of E0. So here, after this distance, when it penetrates inside a medium, suppose after this distance, the original amplitude E0 reduced. How much? Reduced to 37%. Reduced to 37% means from here to here 37, 53, 63. That means 63% reduced, and remaining is 37%. Okay, so at this point the amplitude will be only 37% of E0 we can found. So this distance is called depth of penetration or skin depth, represented by delta symbol. Okay, and you draw this figure carefully. Okay, I am going to zoom this one, and you just pause here this pause the video, draw the figure. This is the unattenuated wave interacted the interface. Okay, here this amplitude, this to this much amplitude OA, here OA equal to E0, that is your original amplitude, original amplitude in free space. Okay, at the surface, when it at the surface, this is your original amplitude E0. When it penetrates at this distance, this is your small z, let this is your small z distance delta, its amplitude remaining 37% of E0. And here electromagnetic wave is propagating along positive z axis direction. Okay, whatever we have been discussed, same thing I have been written, and mathematically we found the delta value for conducting medium. Just watch, I am explaining. Okay, so it is denoted by delta, and its unit is meter. And depth of penetration is also called skin depth, because it is a measure of depth to which an electromagnetic wave can penetrate the medium, which is represented by this figure, in bracket figure. This Fig means figure. Let the direction of propagation of wave is positive z direction. This is your positive, along this positive z direction the electromagnetic wave propagating. And let the wave attenuation be represented by E equal to E0 e to the power minus alpha z. This term already we have been found in our very beginning, where we have been discussed about propagation of electromagnetic wave in conducting medium. You just check this topic, that is your wave propagation in conducting medium or in lossy medium. We found in generalized EYZ is your E0 into e to the power minus alpha z is nothing but called as your attenuated factor. This things is representing the attenuation of, or decreasing of, or reduction of the original amplitude of electromagnetic wave. Okay, the same thing here we have been used. The attenuation be represented by E equal to E0 e to the power minus alpha z, where E0 is your original amplitude of the wave at the surface of the conducting medium. This is nothing but original amplitude, or representing the amplitude in the vacuum. Okay, and alpha is the attenuation constant that we know. Now let 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 z equal to delta. That means delta is nothing but representing the distance at which the attenuation, the amplitude reduced to 1 by eth time. Okay, so here let z equal to delta. Let we have to find out this delta. Okay, let z small z equal to delta. So the equation, attenuation equation, whatever we have been written in the here attenuation, this equation will be E equal to E0 into e to the minus alpha into delta. Instead of z, we just substituted the distance delta. Let this is your equation number 1. From the definition of delta, we have that E0 has to be reduced to its 1 by eth time. So E0 by E, or E equal to E0 into e to the minus 1, right? Let this is your equation number 2. Now we have to compare 1 and 2. We found E0 e to the minus 1 equal to E0 into e to the minus alpha delta. That implies e to the power minus 1 e to the minus alpha delta equal to 1, delta equal to 1 by alpha. Now alpha for conducting medium, if you are going to use, the alpha is nothing but omega mu sigma by 2 root over. Okay, you just check your last class expressions. Here we found this is your propagation characteristics in conductor. Okay, and alpha we found omega mu sigma by 2. Omega is the angular frequency, mu is the permeability of that medium, sigma is the conductivity of that conducting medium, that we have to substitute over here. Then if we are going to substitute this value over here, then delta will be equal to 1 by this much, and it will be 2 by omega mu sigma whole root over. This is your general expression of depth skin, depth of penetration or skin depth for your conducting medium. So just remember this expression, it will help you to solve the numericals. If somewhere it is given omega of the wave propagation, mu permeability of that medium, conductivity of that medium, then easily you can find out the skin depth or depth of penetration. Okay, now likewise this is your depth of penetration in conducting medium. Now you can ask that, sir, could not we found the depth of penetration in dielectric medium? Yes, for dielectric medium, what is the value of delta? That we are going to be calculate over here. It is very, very simple. That we have to find, just substitute alpha value. We know that alpha for dielectric medium is equal to, just go back your note and you can found this is your here propagation characteristics in good dielectrics, and here you can found the alpha value is nothing but sigma by 2 mu by epsilon root over. That is your sigma by 2 mu by epsilon root over. Then depth of skin for this dielectric medium, delta will be, for this dielectric medium, this is for dielectric medium, will be 1 by this much, sigma by 2 mu by epsilon. It will be how much? It will be 2 into this epsilon will be moved to the numerator, epsilon by mu root over, this will be 2 by sigma. Okay, so this is nothing but your depth of penetration or skin depth for dielectric medium. So just remember these two expressions. It will help to you to solve the numericals in your future. So thank you so much for watching this video, and I suggest write down the note and ready for the next class. Next class we are going to discuss propagation of electromagnetic wave, that is your EMW in ionized gases. Okay, so thank you so much for watching this video. Thank you.